Okay, hello everyone. I would like to thank the organizers for the opportunity to give this talk. This is a joint work with Erivelto Borges from São Paulo. And basically, this is a problem about the special class of polynomials over finite fields. I started studying the problem when I was doing a postdoc in São Paulo in 2019. And actually, I got more progress on the problem. So I'll start by fixing some notation. So we fix here Q prime power. So we know that there exists up to isomorphism a finite field with Q elements, which we denote by FQ. Okay, so now we consider one univariate polynomial of degree d defined over the finite field FQ and consider its value set. Right? So we are considering the function induced by the polynomial. Right? I have here FQX, and then I consider the map, right, over FQ. And then I'm just checking the image set, VF. And so by a very basic argument, we can obtain lower bound for the size of the value set, right? So we observe that FQ is always contained in the union of these sets, right? So I'm taking the pre-images of elements in FQ, and I get FQ. Of course, many of these sets will be empty, so I just take the ones that with non-trivial pre-image. And so by taking cardinality on both sides, I obtain this equality. And so it's easy to see, right, since we are over a field, if F has degree D, each element has at most D pre-images, right, because it's bounded by the number of solutions of this equation. And so basically, we can conclude that the value set is always at least Q over the degree of F. And so when this bound is attained, we say that F is a MVSP, right? Minimal value set polynomial. Okay. So before going forward, I'll just give some examples. First, a very simple one. Suppose that Q is odd, and then we consider the square mapping, right? So X maps to X square. And so basically, the value set here will be just, of course, the set of squares of the field. And well, it's not hard to see that the cardinality of this set is exactly Q plus 1 over 2, which turns out to be the ceiling function at Q over 2, right, if Q is odd. So this is an example, and basically follows from the fact, right, that this equality just follows from the fact that this, if you remove the 0 of FQ, this is a cyclic group. So basically, we can generalize this to any divisor of Q minus 1. So this is an example of an MVSP. And also we have another interesting class, which is induced by the so-called linearized polynomials. So P is the characteristic of the field, and then we consider polynomials of this form. So each monomial appearing is a power of P. So by the freshman's dream lemma, right? So it turns out that these polynomials induce linear maps, right? So basically, in this case, the cardinality of the image set, you just use the rank nullity theorem, right? This will be just Q over the size of the kernel of L. So if you want this to be MVSP, this has to be the degree of the polynomial, which just means that this polynomial splits completely over the field. So we have another implicit class. And finally, I'm not going into the details, but we can also check if a polynomial f has the property that its value set falls in a subfield of my big field, and its degree satisfies this inequality, then we also get an MVSP. So I'll just call this family wild because it's it's easy to verify that this is an MVSP, but we don't know like what the polynomial f would look like in this case. Okay. So just a remark here, it's not hard to see that if I pre and post compose my polynomial with affine maps, this doesn't change the degree, might change the value set, but the size will be the same, right? So this is a way of producing other MVSPs from one fixed MVSP. Okay. So these polynomials were introduced like 60 years ago by Carlitz, Lewis, Mills, and Strauss in these two papers. And actually they started studying the description, right? This is a very natural problem. What are the MVSPs, a classification theorem for these polynomials over finite fields? I'm just going to exclude two cases here, the MVSPs whose value set size 1 or 2, so it's constant, or just assume two values. This is actually handled separately, and it's actually very easy. We just do some Lagrange interpolation because the field is finite, so it's easy to handle these two cases. So from now and on, we only consider cases where the value set has at least 3 elements. And so basically in these two papers, they obtained the complete characterization of MVSPs for fields of size p and p squared, right? So fp and the 2-degree extension of fp. So these are the polynomials. They are described up to affine equivalence, so pre and post composition with affine maps. And so for fp, we only have the power maps that we already considered. And for fp squared, we get beyond the power map 2 other maps. This one is just a composition of power map with a polynomial coming from the wild family. And this is just a composition of a power map with a linearized polynomial splitting completely over this field. Okay. So as I mentioned before, the main problem is to characterize these polynomials over finite fields. And basically, we can discuss this problem in two ways, right? So first, we can take an arbitrary subset of FQ and ask if there is any MVSP with this value set, right? So for instance, for x squared, we got that the value set is this guy, right? And for linearized polynomials will be a subspace of my field. So yeah, this is one way of characterizing. We fix a subset and ask if there is any polynomial whose value set is exactly this set. And there is also a second approach that for each extension of FP, we try to characterize all the polynomials with this property. Okay, so this is some motivation why these polynomials are interesting. So there is a work of Storr and Volok. They introduced this definition of Frobenius non-classical curves. So we consider an irreducible plane curve defined by a bivariate polynomial over a finite field FQ. So this curve will be Frobenius non-classical if the bivariate polynomial f divides this expression, right? So we have the partial derivatives of f at x and y multiplied by these two polynomials. And so these curves are interesting, and actually they are very rare, so most of the curves won't be of this type. But they have like some interesting features, including that they might have like a large number of rational points. They also have an interesting geometric property. And basically, if we consider any point on a curve and take the tangent line, it intersects the curve again on a Frobenius conjugate of this point. And in fact, like this definition actually appeared after these two authors. They are trying to give a new proof of Weyls bound on the number of rational points of curves over finite fields. And basically, they obtained a better bound in a case that the curve is Frobenius non-classical. So they basically divide in two classes. For the classical case, they just recover Weyls bound, and for the non-classical case, they obtain something that is at least as good as Weyls bound. Okay, so the connection between these two objects, we have this theorem, I think 2015, of Borges, basically connecting the Frobenius non-classical curves with MVSPs. So we take here f and g, two polynomials, such that this difference is not in this subring. This is, well, most of the cases this will be true. And then we also suppose that the value set of the two polynomials are at least 3. Then if we consider the curve induced by these two polynomials, fx minus gy, so the irreducible components of this curve will be Frobenius non-classical if and only if the two polynomials are MVSPs with the same value set, right? So I'll briefly comment. Well, it's not a proof, or it's quite informal, right? Explaining just why they potentially have many rational points, right? So basically, if we look at the number of xy in fq squared such that fx equals gy, this can be seen as the sum of a in vf of this quantity, x in fq, such that fx equals a times cardinality of y in fq, such that gy equals a, right? Is it easy to see that, right? Because if f equals g, so they are equal to some element of fq, right? So I just stratify by the possible ways. And basically in an MVSP, right? So if f and g are MVSPs, these numbers will be very large, right? So this sum tends to be very large at the end. And we actually have a famous example. This curve is very important in the finite fields setting. We consider q square, right? So we take this curve, xq plus x equals y, 2q plus 1 is irreducible, and actually it arises from these two MVSPs over the field fq, and the value set is just a subfield fq bq. And actually this curve is known to be maximal, right? So it attains the upper bound in the Hasse-Weil bound, and is actually of this type. Okay, so going back to the study of MVSPs, the second paper is a solo paper of Mills. He actually obtained an implicit description of the MVSPs, but it's very implicit. So we have many conditions. So basically, it's not like really possible to describe all the polynomials. But as a consequence, he was able to characterize all the polynomials whose degree does not exceed the square root of q. So basically, this means that the value set is as small as possible, but it's compared to the field is not too small, right? And basically, what he obtained is that up to pre and post composition with affine maps, basically we have to compose the two polynomials I gave in the very beginning, the basic examples. So we have a linearized, splitting completely composed with a power map. And also, in the end of the paper, he suggested that up to the wild family, I don't know if you guys remember, there was a third family of polynomials. He mentioned something like it's highly unlikely that there will be anything else. So apart from the wild family, all the polynomials should be of this form. So composing a linearized with a power map. And so in the paper, as I said before, there are some partial description of the polynomials, but a very interesting thing that appears, it's a differential equation that these polynomials must satisfy. So basically, here it's supposed to be larger than 2. So if we take an MVSP with value set having at least 3 elements, and we consider T the vanishing polynomial of the value set, right? So I take out the elements in the value set, consider this polynomial. We see that if we take this composition, T composed with f of x, if I evaluate this composition at any element of fq, I get 0, right? Because f of anything will be something in the image set, which is a 0 of t. So this polynomial is naturally divisible by x to the q minus x. And basically for MVSPs, this is exactly x to the q minus x times the derivative of f, right? I'm not going much into the details about techniques, but this equation is very important, right? Most of the results we have, it goes through this differential equation. Okay, so in a more recent paper in 2013, these two authors, they obtained a complete description of the MVSPs, now fixing the value set, right? Suppose that the value set is a subfield. And so what's the idea here? Basically, if I want my value set to be a subfield, this polynomial t of x will have this form. And this is, again, a linear polynomial, right? So this differential equation now is a linear differential equation. So in particular, we conclude that the set of solutions is a vector space, and so basically they are able to describe this vector space. There's a lot of combinatorics. There is the Frobenius automorphism plays a role, and we can actually describe the set of all polynomials whose value set is a subfield. Okay, and an interesting point in this work is at the very end, they are able to construct polynomials that do not agree with Mills' conjecture, right? So he basically conjectured that if the value set is small enough, then it should fall into a wild family. And basically, this is the first instance that we can get is an extension of degree at least 6. 5 and below, it's true what he said, but for a 6-degree extension, we can get a very simple counterexample, and from that, actually, we can construct infinitely many counterexamples. Okay. So a more recent result in 2021, we were able to characterize all the MVSPs over fields of size p cube, right? So I'm not going much into the details. Basically, it appears 2 easy families that appear in the case of fp square, but also we get a new family that basically relies on taking a power of a polynomial, which is also an MVSP, but now the value set being the subfield fp, right? And in fact, we could only get this result because in 2013, there was the description of MVSPs whose value set is a subfield, right? So basically, these two approaches trying to characterize the polynomials by field extensions or by value set, they are actually connected, right? So, and also as a consequence, we are able to characterize a family of Frobenius non-classical curves. In an earlier work of Borges, he provided a complete characterization of the curves. They are also of the type y to the n equals f of x, whenever n is at least q cube minus 1, right? So as a result of our classification theorem here, we are also able to cover the remaining range, right? So we can go this direction. So here's the description, and basically, it appears the polynomial in this third family. Okay, so far we've seen that there are three main types of MVSPs, right? So those whose value set is a subfield, studied in 2013. I'm calling projections just for simplicity. We have the linear polynomials and the monomials, right? And as we have seen, if we take suitable composition of these polynomials, we may also get MVSPs. And so this is a more recent work. In a few weeks, we're going to put the paper on archive. We have some progress on the problem. So first, we were able to characterize all the possible value sets for an MVSP. So basically, up to affine equivalence. So we make some changes of pre and post composed with linear polynomials. We conclude that the value set must be a vector subspace of FQ power to some integer. And the converse is also true. For each set of this form, we are able to explicitly find one MVSP with this value set. And actually, by considering this result, we are motivated to propose a conjecture towards the complete characterization of these polynomials. So basically, in the Mills seminal paper, he considered a power from the Wild family must be a power composed with we take a linear polynomial and then take a power, right? And so basically, what we believe is that apart from a projection, this is true, but we might also have a projection here playing a role, right? So I first start with FQ, and then I project in a subfield. And then I take a linearize it. This will send the subfield in a subspace, and then I take a power map. Right? So we have three maps here. And actually, this is reasonable because in Mills' paper, he considered the value set being of size at least square root of Q. If I have a non-trivial projection, right, this field FBQ will be of size at most square root of Q, right? This extension has degree at least 2. So it's something that, in fact, agrees with what we know so far on these polynomials. And also, we were able to prove that the conjecture holds when V equals 1. So the value set is just a subspace. There is no power. And more than that, using our characterization, we actually can get as a consequence that if the conjecture is true, with our result for V equals 1 describes all the possible polynomials. And also, using some character sum techniques, we are also able to cover the case P4 now. And the conjecture is also true. Okay, so these are the references, and I'll stop here. Thank you.